Hey folks. All right, this is the second to last video. That means this is like the second to last time you're going to see me jam out before talking about CHEM. Okay, so as you can tell by the slide, we're getting into more on this UV Viz. Hopefully this is still familiar to you all from instrumental. I was distracting myself with the music. I had to stop it. I was going to do something cool where I talk through the music, but I was getting distracted. Okay, so here we go. So I think a lot of this stuff should be familiar to you all, particularly for those of you that took instrumental analysis. But all the same, we're going to go through it. Okay, so these are our fates of electronically excited states. And so as you can tell, there's a lot of things that can happen. So let's just talk about them one by one. So we've got stimulated absorption. And so that's exactly what it sounds like. Transition from a low energy state to a high energy state. And so absorption is proportional to the intensity of stimulation. And as we've talked ad nauseum, that's related to the transition dipole moment operator. Okay. So then we have stimulated emission. And so that's transition from a high energy state to a low energy state at the same frequency as absorption. Okay. So emission is proportional to absorption. All right. And so these two things right here are often what create either absorption spectroscopy or emission spectroscopy, most notably in elemental composition analysis, right? Doing flame AA, for example. Okay. So we have spontaneous emission. And so that's the transition from a high energy state to a low energy state at a different frequency as the absorption. Okay. And so as you might guess, spontaneous emission can be classified as either fluorescence or phosphorescence. Okay, and we'll talk about that momentarily. So there's intersystems crossing. So that's a non-radiative transition between states of different multiplicity. Okay, so non-radiative means that it's transitioning to a different energy state without the release of any light. Okay. And so oftentimes that transition between these two states of different multiplicity is occurring where the states have good overlap, okay, and also where they have very similar energy. And it's important to note that because this is different multiplicity, this is pretty rare for intersystems crossing, okay? And so when things are pretty rare, they can be kinetically slow, okay, as we'll discuss. So internal conversion is a non-radiative transition between states of the same multiplicity. So this is more common than intersystem crossing because the multiplicity is conserved. Okay, so now our two spontaneous emissions can be classified as fluorescence or phosphorescence. So fluorescence is stimulated absorption followed by spontaneous emission at a lower frequency than the absorbing frequency. Okay, so in other words, the light that is emitted in fluorescence is at a lower energy than the light used for absorbance. Okay, and so multiplicity is conserved. So we only do triplets to triplets or singlets to singlets, and the fluorescence lifetime is very fast. So that means the excited state decays really quickly. Okay. Phosphorescence is spontaneous emission at a lower frequency, similar. Okay. However, multiplicity is not conserved. So this is where we get a triplet to singlet or singlet to triplet. And because of this, lifetimes are very slow, as this is a forbidden process, right? Just as we talked about with intersystems crossing, okay? And so what we start to see in molecules, oftentimes forbidden processes in molecules can be observed, albeit at very low intensities or very slow rates. And the reason why these forbidden transitions can be observed in molecules and not atoms is because molecules can rotate and vibrate and contort themselves in a way that might allow angular momentum to be conserved. Atoms can't do that, right? An atom has a very rigid shape and structure. Molecules, on the other hand, are kind of floppy, right? And they can be distorted and perturbed in a way that allows these forbidden processes to occur. So moving on. So this is a look at intersystems crossing, right? And so the idea here is if we have stimulated absorption, as shown in the blue line, okay, we can see that intersystems crossing is really only going to be observed when we have a singlet state and a triplet state both lying in the same energy level, okay? Or not, I shouldn't say same energy level, but both have a similar energy, okay? So you can see the triplet state is slightly lower in energy than the singlet state, but all the same, they're kind of right on top of each other, okay? And particularly where the intersystems crossing is occurring, it's showing that it's occurring at these levels. In this fictitious example, intersystems crossing is occurring right there because those two upper lying vibrational levels are practically right on top of each other, okay? So there's no penalty for that transition to happen, okay? So where we see this occurring, and then of course, what's going to happen in this example, there's now an electron in this triplet state as indicated by the green arrows. All of these little arrows here are what we would call radiationless decay. So those vibrational states can relax one state at a time, right? We remember nu still has to change by plus or minus 1, but those can be occurring through what we call inelastic collisions. So collisions with neighboring molecules that impart that excess vibrational energy and cause this molecule to relax, okay? So if the radiation decay occurred from the triplet to the singlet, that would be phosphorescence, right? But if it occurred from a singlet to a singlet, for example, that would be fluorescence. And what would we would observe if we could keep track of the emission intensity of our chromophore over time, we would see the light being emitted as a result of fluorescence would decay very quickly. The phosphorescence, on the other hand, would be very slow. So as a result, I'll just say biology has really figured out how to take advantage of phosphorescence. You might have heard of these particular critters that live in caves that hardly ever see any daylight at all, okay? And so those critters that undergo bioluminescence, what that really is phosphorescence, because the phosphorescence emission intensity decays slowly. And if you were trying to biologically engineer yourself to give off light, you would really want to be undergoing phosphorescence, right? To have that nice long-lasting emission intensity. So often when you hear about bioluminescence, it's really phosphorescence that's occurring there, okay? So moving on. So here's a look at our potential energy profiles as well as what a spectrum would reveal. And I think this is really cool to see those two things side by side. So here, if we were looking at the absorption, okay, and I'll first note by pointing out this 0, 0 line right here. So what that 0, 0 line means is we're talking about nu equals 0 in the ground state. So often there's a double prime for the ground state. And nu equals 0 in the excited state. So I'll note that these are nu prime and these are nu double prime. Okay, and so what that means is this peak right here, this 0, 0 peak, that actually corresponds to going from nu equals 0 here to nu equals 0 here. Okay, and right, doing that vertical transition, we recognize that it will be possible, albeit it will occur with low intensity, based on this particular example that I'm showing you. And we can see that here, right? This is one of the lower intensity peaks. And so that 0, 0, right, corresponds to this peak right there. And so then if you think about it, for the emission intensity that you would observe, so notice now that there's another fluorescence peak that occurs right there, okay? And so that's from going from this, so it's not quite showing you this arrow right here, because it's actually going, again to the 0, 0 line, all the way down there. And once again, for the fluorescence, that occurs at low intensity because we recognize the wave function will look something like this, but there is a small yet finite amount of tunneling that can occur past that potential energy well that gives rise to this very low observed intensity. So now what you notice, each one of these peaks, right, corresponds to a new vibrational level within the absorption spectrum, okay? And so, for example, this very next one right here would correspond to going up from 0 to 1, so going up to that extra level, okay? So I'll say that's 0, 1. And then the next peak would correspond going to 0, 2. And as you can see on this diagram, 0, 2 definitely occurs with some nice overlap, right? So if this is level 0, 1, and 2, you can see right here definitely where it's hitting that turning point, okay? That's where it's got the best overlap. So that's where it's got the highest intensity. And so now what you can see on this diagram, it's pointing out here this A right here, which is pointing out the spacing between each one of these vibrational levels. Well, as it turns out on the absorption profile, that distance A corresponds to, I'll say, delta nu for the excited state, right? Because as each one of those goes up, that difference that you're seeing is really the difference between an excited state vibrational level, okay? And now what you're seeing right here, the peak-to-peak distance on this fluorescence profile, B, is going to give me the change in frequency, or the vibrational frequency, for the ground state, right? Because as you can tell, as each one of these goes down, we could go 0 to 0, or we could go 1 to 0, or excuse me, rather 0 to 1, or 0 to 2, etc. Okay, so in the absorption profile, you can see the vibrational energy levels for the excited state. In the fluorescence profile, you can see the vibrational energy levels of the ground state, which is pretty cool. And this, the way this works out, it's because of this fictitious example right here that has this nice Frank Condon vertical transition overlap. Okay, not all molecules have nice overlap like this. And I think I have a picture of something like that next. Yes, so just to remind you, right, when we're talking about excitation, from the ground state into all of these upper lying levels, we can see, each one of these little peaks corresponds to those vibrational energy levels. However, as soon as we're out of the well, we're just going to get nice continuous, what we call continuum absorption, which is really just related to unquantized translational motion of the photo fragments, right? Because recall, once we're outside of this well, we have separate fragments right here if our molecule was AB, okay? So we can also get what's often referred to as predissociation, where if, let's say, there was a repulsive state, okay? So I'll say R, so some anti-bonding state, right? We can see how excitation to one of these levels right here could then lead to, an intersystems crossing or internal conversion, depending on if the states are the like multiplicity which could lead to then photo dissociation, right, to photochemistry. Okay, so that's showing you another thing that can happen to these excited states. So here I have a real example of a molecule that actually has one of these nice overlaps that what I've been talking about. And so this is the absorption spectrum. So you can see it's the UV vis absorption spectrum of the CLO radical, so the hypochlorite radical. And you can see that it has absorption between, about 230 nanometer to 320 nanometer. And this is the actual absorption spectrum. So it actually has this continuum absorption up to about the lambda max at about 260. And if we look at the potential energy diagrams, right, you can see here's the absorption spectrum on its side right here. Okay, I'll say 90 degrees, right? There's the absorption spectra. And you can see the vertical transition from the ground state to this upper lying state occurs right at the top of the well. So this is actually a really cool example of something that has that perfect overlap, okay? And so we recognize, of course, there's vibrational levels in this well, and there's vibrational levels in this well, okay? And so what you can see here, this peak right there, that's what's giving us that value at about 260 or so nanometers, right? So that's about 260. And then now you can see there's a whole barrage of vibrational levels that are accessed, okay? And so I noted this here, VF and VI. So that 12.0, that means VF is nu equals 12, something like way up there. And then the 0, right, corresponds to this nu equals 0 down here. So I'll go back and put the double prime and the single prime, right, to be consistent. Single prime in the upper, double prime in the bottom. That's just another spectroscopy nomenclature that is used. I'm not too concerned about you memorizing that nomenclature. And so then what you can see, really cool with the CLO UV vis spectra, you can see a peak for each one of those vibrational energy levels, okay, which is really neat. And so, of course, then the difference, I'll just highlight like one peak here. So each of these will be, the same difference, right? And that difference will have a value of nu tilde, right? Which is the vibrational energy level, right? That has to do with the force constant and the reduced mass and so on, okay? So very cool, very serendipitous to have a real molecule that displays this perfect Frank-Condon overlap of continuum absorption on one side and what we call banded vibronic structure. So that's the confluence of the electronic energy levels and the vibrational energy levels. Okay. So moving on. So I want to talk about just some common transitions we see in larger molecules, because you may have noted using these potential energy diagrams works really well for simple molecules like CLO, right? But when we get into more complicated molecules, that's less straightforward, okay? So commonly observed in larger molecules, so I'll write commonly observed transitions in, quote, larger molecules. And you can see here I've got acetone as my large molecule example. Okay, so pi to pi star and N to pi star transitions are very common in UV vis spectra in large molecules. In fact, I would wager that's probably the only type of transition you've seen in your experience with UV vis. Okay, so typically you need to have some degree of conjugation, or even just some very simple pi bonding system. So you can see here with my example using acetone, very simple pi system, just one carbonyl, okay? And so recall the pi state is the bonding orbital, right? And then way at the top up here is pi star. So I'll redraw this diagram like this here, where we're not even focused on the sigma bonds. I just want to focus on the pi and the pi star, the bonding and the anti-bonding, okay? So that's a very common transition to see in absorption spectra, pi to pi star. And typically that occurs way down in the UV, okay? So pi to pi star is almost always UV. And you can see for acetone, that occurs at 195 nanometers. So that's a very high energy transition, which makes sense when you think about these MO diagrams, right? Well, then what is an N to pi star transition? Well, an N, represents a non-bonding orbital. So typically that's coming from a lone pair, okay? So our N to pi star, as you can tell from this diagram, will occur at a lower energy. And you can see for acetone, N to pi star occurs at 274 nanometer. And here we're seeing those diagrams of the molecules. Oh, excuse me. So what ends up happening, so there's something really interesting that happens with pi to pi star and N to pi star. So you notice the pi to pi star is occurring at a much higher intensity than N to pi star. And that's because pi to pi star transitions are allowed and N to pi star transitions are forbidden. And that's forbidden due to the conservation of angular momentum. So it's a spin forbidden transition. And that's related to the fact that if you look at the pi bonding structure showing constructive overlap of p orbitals here, and then the anti-bonding shows destructive overlap, okay? The change in angular momentum from pi to pi star can be conserved with the photon. And I'm not going to get into the quantum numbers, I'm not going to get into the details, but it has everything to do with the geometry of the pi bond and the pi star bond, okay? So now the non-bonding electrons, and in this case in acetone, we can see those are the lone pairs over oxygen. Those are in the same plane as the CR bonds, which do not allow conservation of angular momentum to transition from these non-bonding electrons to the pi star, okay? So that should be forbidden. But you can see that it's not forbidden, it's actually observed. And the reason why it's observed is because acetone, like all other molecules, is kind of floppy. It can distort, it can rotate, it can vibrate. The rotation only in the gas phase, right? But certainly the vibrations such as the symmetric stretching, the asymmetric stretching, and the bending motion particularly, okay, will put those non-bonding electrons out of plane of the CR bonds and into the plane of the pi star. And so that means occasionally there is an orientation of this molecule that will allow a transition from the N, non-bonding orbital to the pi star anti-bonding level, okay? And that's why you see it occurring at very low intensity. So now what happens as the molecules get bigger? Well, it's a particle in the box phenomenon, right? So as molecules get bigger, I'm sorry, my handwriting is really failing here at the end of the semester. So as molecules get bigger, these transitions will shift to longer wavelengths, okay? So for example, nitrate, NO3 minus, has a really nice pi to pi star and N to pi star UV vis spectra. And it looks almost identical to this acetone spectra, although it's just shifted down by about 100 nanometers because nitrate is just a little bit bigger than acetone, okay? So this is pretty cool. So if you've ever seen a UV vis spectra where you have really, really high absorbance in the UV, and then you get a secondary peak, perhaps into the visible, but also still maybe in the nearer UV, you know that that's pi to pi star for the big peak and N to pi star for the little peak. Okay, so this is very common in molecules. Let's see, the final thing, I've got this little Jablonski diagram. I know you guys have done these before in instrumental. I know not all of you have taken instrumental, so I'll just kind of briefly introduce these Jablonski diagrams as a way of really organizing all the photophysical, radiative, and non-radiative transitions. And so what I want you to do on your own, maybe in good preparation for the spec super quiz, see if you can identify what all of these transitions are, and I'll label what they are in the next video. Okay, folks, that's all I got for this video. Our very last video will be all about lasers. Hasta!